Hey guys, welcome back. Let's get to the next problem, which is 1 knapsack. I hope you're familiar with this problem now, as we have already solved fractional knapsack with greedy approach in greedy algorithm section. In knapsack problem, we are given a knapsack with capacity W and weights and prices of n items. So we need to put these items in knapsack such that it won't exceed knapsack's capacity and we get the maximum profit. Now the difference between these two is that with fractional knapsack, we're allowed to put fraction of items in the bag, right? But with 1 knapsack, we have to put the complete item. So there are just two choices. You can add the item or you cannot add the item. For example, you have knapsack of capacity 10 and items are of weight 7, 4 and 5 and prices 15, 8 and 8 respectively. Now if we solve it with greedy approach, we will sort items as per their cost ratio. So it will pick the item that give us maximum profit with minimum weight, right? And that is the item 1. So the value will be 15. Now further you can't put any other item in knapsack as knapsack don't have enough space and you can't put fractions of item. So profit remains 15. Now think, is this the maximum profit that we may get? Nope. The optimized solution would add item 2 and item 3 so that the profit will be 16. So clearly this time greedy fails. Therefore we need to take different approach and that approach is dynamic programming. Let's go with it. Let's first try to solve it with recursion. We have n items and we have two choices. Either we can include the item in the solution or we can exclude it. We do calculate profit in both the cases and go with the choice that's having maximum profit. So you include item 1 and calculate profit. How? You take the price of item chosen and check for the rest of the items. Can you include them in the solution after including 1? Clearly you cannot. So capacity of knapsack is reduced to 3. So profit becomes 15. Now what if you exclude item 1? Then you just check for the rest of the items. Clearly, if you don't include 7, you can add these two items and get the maximum profit, which is 16. So there you got your subproblem. For n items, if you include the last n minus 1th item in the knapsack, you calculate profit by taking price of that item and the profit of remaining items with remaining capacity. That is price of n minus 1 plus recursively you're calling the same function for the remaining items with the remaining capacity. That is your first subproblem. And if you don't include the item, profit will be the profit for remaining items with the same capacity, right? So this is our another subproblem. But we have to choose the maximum and we check with which approach we are getting maximum profit. So the recurrence will be maximum of price of current item plus profit for remaining items with capacity W minus current item's weight, where the weight of the item must be less than or equal to the capacity. This is the first case. And the second one is the profit of remaining items with the current capacity. And then we're gonna choose one which is maximum of both. Let's see the complete recursive solution. So either we include the item or we exclude the item, right? So here see, if the weight of the current item is equal to or less than the capacity, then we can include it, right? So we are including the price of the current item and then we are recursively calling get max profit by eliminating the weight of the current item for the remaining elements or for the remaining items. So this is the case when we are including the current item. But what if we exclude the current item? So we have to calculate that profit as well. So here we are calculating get max profit for the remaining elements or for the remaining items with the current capacity. And then we find out the maximum among these two, and then we return it. So what is the base case for this recursion? It is either when the capacity of knapsack becomes 0 or we are left with no items. In that case, we will simply return 0. So with this approach, or with this recursive approach, the time complexity will be exponential. Why? Because there might be overlapping subproblems. That function will compute again and again. Let's see how we can solve it using dynamic programming. So first approach is top to bottom, or we can say recursion plus memoization. Instead of solving overlapping subproblems again and again, we may create an array to store the profit that we calculate. Let's move forward to top to down. Now let's see how we can memoize it. So we need to take an array that can store result at each step, right? And as you know, there are two parameters, n, which is number of items, and w, which is capacity of knapsack, which are changing at every iteration. So we need to take a 2D array to store result of every recursive call. Like here, we have n equals to 3 and w equals to 10. To keep all results stored, we take a 2D array of n plus 1 multiplied by w plus 1 dimension, and we initialize it with minus 1. And as we made recursive calls in our naive recursion approach, we'll do the same. To fill the knapsack of capacity 10 with 3 items, we check values for n equals to 3 and capacity equals to 5. And now we check if the value is already calculated. We can see it's not, as there's minus 1 placed there. So in that case, we make recursive call and calculate profit for it. This continues till when we reach to our base case, which is if we are left up with 0 items or 0 capacity of knapsack. So we update that cell as 0. So now the recursive call f11 has its value 0 stored in the array. And in order to calculate profit for f25, we add price of second element, which is 8, right? And since f15 will also be 0, so we take 8 as the maximum profit among both for the subproblem f25. And then we update the cell to 5 as 8. So this is how we store result of every cell in this array. So that if similar subproblem ever occur, then that can be picked up from the array as it's already calculated. Now let's see how we implement the bottom-up approach to solve this knapsack problem. So we create a 2D array with similar dimensions. Difference is, in bottom-up approach, we start filling the array from the smallest problem. So we iterate through the array when items are 0 or when the capacity of knapsack is 0, which was the base case when we implemented the top-down approach, right? So here we update 0 in the array. So initially when item is equals to 0, we update 0, and similarly for item 1, when capacity is 0, we update 0. Now for I equals to 1 and j equals to 1, which is when the capacity of the knapsack is 1 and we have to fill the bag with exactly one item. So to fill this, we check if the first item can be added to knapsack. We can see it is having weight 7, so it cannot be added as the capacity is 1. So we exclude it and check fill the cell with profit for remaining items, that is for I minus 1 comma j, which is the value for 0 1, which is equals to 0. So we fill it with 0. Next, for capacity 2, again we cannot add I minus 1th element, that is the first item. So we exclude and update the profit of 0 second cell. This will continue till j is equal to 6. Now when j becomes 7, we have knapsack of capacity 7, right? So this time we can put one item, item 1, with weight 7. So we check profit when we include this item. To do that, we add the price of this I minus 1th item to the profit of remaining items with the remaining capacity. That is for I minus 1 items with capacity, that is current capacity minus weight of chosen item. So we take price for 0th index, value for 0, 0, that we have already calculated, which is 0. So we add 15 and 0. This is the profit when we include this item. Now when we exclude this item, the profit will be the profit for remaining items, that's value 0, 7, which is having value 0. So max profit for this subproblem will be 15. Hence we update this 15 at the current cell. Similarly, we check for capacity 8, 9, 10 for item 1. The max profit for all these subproblems will be 15. Now next iteration. When we check for the second item in the knapsack, first for the capacity 0, that will be 0. Next check if I minus 1th element can be added in the knapsack. We can see item second is having weight 4, so it cannot be added in the knapsack. Hence we exclude it, and then we check for the profit for the remaining items with capacity 1, that is 0. So we update it with 0. Similarly, till j equals to 3, we update 0 as we cannot put the second item in the knapsack of capacity less than 4. And for capacity 4, capacity equal to 4, we check if we can include the second item. Yes, we can. So we calculate profit by adding price of this item to the profit for the remaining items of capacity 4 minus 4, which is 0. So hence profit gets 8. And if we exclude this item, we get profit 0. So clearly for this problem, profit 8 is maximum. So we update it with 8. So this continues for capacity 5, 6, the profit will be 8. And for j equals to 7, it checks for the profit. When we include second item, it is 8. And when we exclude it, we check for the profit for the remaining items with capacity 7, and that profit for 1, 7 is 15. So clearly here the profit 15 is maximum. That means in bag of capacity 7, if we exclude this item and go with previous profit, we get maximum profit. So we update 15 here. And again, same will happen for capacity 8, 9 and 10. Maximum profit will be 15. We continue this to fill for item 3 when capacity is 0, 1. We cannot include item as it is of weight 5. So we exclude it and take the profit for 2 items, which is 0. So we fill 0 here. Similarly, profit 0 will be updated for capacity 2 and 3. And for capacity 4, we still cannot add the item with weight 5. So we exclude it and update the profit for remaining items, which is 8. So this continues.